So that's one of the issues that we want to sort out with regard to Linux. And the way that is done is, rather than sort of saying that let's go and change it in the kernel itself, what people said is, look, for the most part people are not really interested in real time. The only thing that I really care about real time is probably responding to key presses and the mouse, and there are a couple of other ways by which I can handle that, probably by giving them high priorities. But I can't give everything high priorities and make sure that I sort of guarantee latencies. So instead there is a separate patch set, or rather set of changes to the Linux source code itself, which is called the preempt RT, which is the preemptible real-time patch set for the kernel, right? And what this does is that it is actually a change to the Linux kernel itself. It is not what you would normally be running on any of your systems. Very unlikely that you would find a desktop or a laptop that actually runs the preempt RT version of Linux. And the reason is that even though it makes certain things real time, it can make other things slower or less efficient, right? So throughput, for example, is usually sacrificed when I'm having all these conditions which allow me to get high real-time performance. Okay. What it does is it makes the kernel fully preemptible, meaning that there are very few sections that can actually make the system just wait, and you have to sort of arbitrarily long wait for a response, right? There are a number of different things that are used over here. One of them is, we have already talked about the idea of using spin locks. The basic idea of a spin lock is that you are in a critical section, you want to wait for a resource, you just spin over there waiting for that resource to become free. It's sort of like polling, but the point is that you are doing it in a very, very constrained and minimal environment over there, right? Now the problem with that is you are still completely stuck over there until the spin lock is resolved, right? So rather than that, they actually use some other kind of approaches which are called RT mutexes, which are a variant that have less overhead but are usable only in a very specific kind of context, right? They allow preemption in certain critical sections, right? Even when you are in a critical section, they can allow preemption of that particular task, right? There is an important problem called priority inheritance, right, that you need to deal with over here. The basic idea being that you have two tasks, one with low priority, one with high priority, and the thing is that if a low priority task currently holds a lock, right, and that the low priority task is very long running, then the high priority task that comes in cannot run because it's waiting on that lock. Now high priority tasks usually also have timeouts associated with them. They say I can't wait indefinitely, right? So if something hasn't responded, I'm going to reset the system or do something very drastic, okay? So instead what you do is you say, okay, right, if the low priority task is stuck over here, right, has got this lock and is waiting, I want to make sure it gets done as quickly as possible. So let it inherit the priority of the other task that tried to interrupt it or to try to preempt it, so that it can resolve the lock as quickly as possible and get out of the way, okay? So there are a number of issues that come in. The point I'm trying to make is these are not things that I'm going to cover in a lot of detail, that we can these are sort of outside the scope of what we can cover over here. But there are a number of issues that come up when you try to resolve the problem of priorities, preemption, and so on, right? And it's very easy, if you are not careful, to get into a scenario of deadlock, meaning that something is waiting on a resource that is locked by someone else, and that someone else in turn is waiting on something where this, probably on the other thing that's asking for it, right? So there is like two things that are dependent on each other and neither one is able to move forward, okay? Deadlocks are very easy to create in these kind of concurrent systems. Any concurrent system has the potential to have deadlock, right? Because the order in which you do things can potentially change the way that the system moves forward. And designing such systems is extremely hard, and proving that they will not deadlock and will never get into a problem can be in certain cases even impossible, right? But the point is that this particular change over here helps to reduce worst case latencies, right? Another change that is made is, rather than having IRQ handlers that sort of do all the work themselves, they change it so that the IRQ handler, essentially all that it does is it basically triggers a thread. It starts or activates a certain thread which is going to run in the regular process context and not in the OS kernel context, right. So, how does that help? Once again, the problems come only when you are in the OS kernel context, right. That is when you can't interrupt things, you cannot, you have like high priorities and so on. So, if you can minimize the time that you are going to be in that context, you can go out into a separate thread which can in turn be preempted, right. So, by sort of reducing the work of the IRQ handler to just sort of triggering off that thread, you can improve the latency of an IRQ response, right. So, these are like two things that can be done. Yet another one is using the use of so called high resolution timers, right. So, we have already seen in the past that very often even in the kernel drivers, we tend to sort of measure time in terms of jiffies. Now, a jiffy sounds like it's a very short unit of time, but actually in practice it's like probably on the millisecond time scale, right. And the reason why this is chosen is because this is a good number for interactive use. But 1 to 10 milliseconds can be a very long time for a computer, it's like millions of clock cycles, right. So, in that case what happens is that they also use so called microsecond precision high resolution timers, right. So, these high resolution timers allow a finer granularity of scheduling, not quite at the, well, at least at the tens of microseconds scale potentially, right. So, rather bringing it down from 1 millisecond probably by a factor of 10 or more, okay. So, it allows you to have more fine grained control over the resolution that you are talking about. So, all of these things are introduced, the primary purpose being bound the worst case latency, put a limit on how bad the worst case latency can be and make response times predictable, right. In the process, of course, one of the things that they have to do is that you need to make sure that low priority tasks cannot sort of hold up high priority tasks. So, you make sure that if there is a high priority task that is coming in and is dependent on something used by the low priority task, you increase the priority of the low priority task, that is priority inheritance, right, so that it clears up very quickly, right. You increase it all the way to the priority of the high priority task in general, that is priority inheritance. But as I said, there are trade-offs, which is why you do not find preempt RT everywhere on laptops and desktops. There are, one of the main things is lower average throughput, right. So, for let us say high performance servers and so on, this is probably not a good thing to have, right. And you tend to have more context switches as well, because as we can see there are many things that can be preempted, that is the whole point of the name, right. Pretty much any context it is possible to preempt and have something else come in and say, okay, schedule another task to handle it later. Usually results in more context switches, which is not necessarily a good thing. So, yes, there are benefits, there are trade-offs, but both of them are sort of made possible in the context of the preempt RT patch set, right. So, to sort of summarize what the impact of something like this would be, standard Linux is throughput optimized, right. It is very good for batch processing. Let us say you are trying to do database queries or generating web pages or things of that sort, where there is a large amount of computation being performed in bulk. It is also good with caching and lazy operations, where essentially the demand paged kind of memory management, where you can allocate a large amount of memory and as and when the memory is required, it is sort of brought into the system, right. RT Linux or preempt RT would suffer from that as well. Demand paging is sort of the opposite of what you want in a real time setting, right. So, ideally you try to sort of actually allocate exactly as much memory as you need and lock it physically in the RAM, right, so that nobody else can access it at that time. So, there are changes in that as well. The average performance tends to be very large or very good. It is particularly good with things that involve the network stack or file IO, things that are by themselves fairly non-deterministic and can have a high degree of variability, right. You can't guarantee that your network is going to give you like exactly so many bytes per second, it is probably going to be bursts of packets. Similarly, file IO you might have to seek across different parts of the disk, again adding to the latency. This is just a schematic chart, this is not actual data, right. It is just sort of showing you that you can have variable latency, right. Sometimes as time goes on over here, right, you find that the latency is like fairly low, but sometimes it can become fairly high, then it again decreases, again increases. There's a maximum to minimum variation is fairly high over here. What the RT optimized version of preempt RT Linux, right, this set of patches to the source code is focused on the idea of immediately responding. So-called eager operations, things which are not sort of doing demand paging, which try to, as soon as you request a certain operation, it is done, right? Processor gets on it, tries to do the task and finish it as quickly as possible, right? The most important is that they manage to bound the worst case latency. Now, where are these things particularly important? Let's say that you have things like data acquisition or motor control. These are places where you actually have tight limits on the latency that you can accept, right? If you are sort of sending out pulses to control the movement of a motor or of anything else, right? It might also be like some high precision equipment. You cannot afford to skip a particular time interval. You have to make sure that you respond at the right time, right? And make sure that the data acquisition does not drop a sample, the motor control is not going to skip sending out a control pulse, right? All of those are ensured. As you can see, the max and min latencies in this are as close as possible, right? Once again, this is a schematic chart, it's not actual measured data, but the idea is that you want to keep these as close as possible, okay? Now, as you can see, the places where you want real-time Linux, if you think about it, motor control, data acquisition and so on are unlikely to be things that are working at extremely high rates. You are probably talking more in the kilohertz or probably hundreds of kilohertz to possibly megahertz range, but probably not in the gigahertz ranges, right? At that point, if you are actually trying to do something control at the gigahertz range, you pretty much should not be having an operating system, but going directly to the processor and making sure that you have tight control over every single operation that it executes, right? Or possibly not even use a processor in the first place. But if you have something which is in the hundreds of kilohertz to low megahertz ranges, this can be very useful because it manages to bound the worst case latencies in the microseconds ranges and at the same time give you all the benefits of tight control over what you need.